You know, we always hear people talking about virtual machines versus containers, but let's be clear, right from the start, they both have their place. They actually do different things, even though we quite often hear them being equated together. VMs tend to be a little heavier or a lot heavier than containers, but they both are used in a modern data center. There is a need for both of these. Many people wonder, what are the differences between virtual machines and containers, and how do they fit into our modern cloud-native way of building and architecting applications? Well, we're going to try to answer that question for you in 4 parts. First, let's talk about some of the differences between virtual machines and containers. On the left, we will look at virtual machines, which are often just called VMs. There's a good chance most of you will have used them because they've been popular for quite some time. Next, we'll look at containers over on the right side, and I would not be surprised if you do not have a good understanding of them yet because they're much newer. If you are familiar with them, then it's quite likely you are involved with app modernization or microservices. The first thing that we want to make clear is the level at which virtualization happens. These two technologies are different ways of achieving virtualization. Virtual machines employ hardware virtualization because it happens at the hardware level. So we're going to start with the hardware down at the bottom because these are computers. And what we have on top of the hardware is what's called a hypervisor. In the hypervisor is the technology that is responsible for creating these virtual instances of each of the components that make up our virtual machines. We're talking about processors, RAM, storage, and network cards. All of these things are being virtualized by our hypervisor. With containers, we start again with the hardware down at the bottom, but we build them up a little bit differently. On top of the hardware, our kernel sits, which is what helps our software and hardware talk to each other. On top of our kernel, we have our operating system, and we call it our host OS because it's going to be what is hosting all of our containers. Then on top of the operating system, we have each container. Here we're showing numerous containers. We can run many dozens of containers in one instance of an operating system. That is why this is called operating system level virtualization, because it happens at the operating system level. It is a software approach, whereas with our virtual machines, we're working at the hardware level. The VM model illustrated here is known as a Type 1 hypervisor, or some people refer to it as full virtualization or full system virtualization. The second thing to be aware of is the type of isolation that's being achieved. With virtual machines, we are achieving isolation of machines. Let's imagine in our base layer, we have one server that is in a rack somewhere. However, we want to take our resources and split them up so that we get as much use out of that server as possible. We take our hypervisor and we make VM1, VM2, VM3, and so on. we have taken one physical machine and increased our usefulness by making what appears to be multiple different machines, and each machine is relatively independent of each other. Essentially, they don't really know about each other. When we interact with them, we wouldn't really know they were virtual machines. They simply appear to be different servers which could be located anywhere. Whereas with our containers, we are dealing with process isolation. Let's make sure we're very clear about this. When we run applications on our laptops, they are nearly always running in the same environment. They can all see what is running at the same time, and in many cases, they communicate with each other and share resources. However, when we are dealing with containers for the sake of security, we make sure that applications can only see what is absolutely necessary for them to run and nothing more. What containers allow us to do is share the same operating system and the same kernel, but it appears to each container as if they have their own operating system and only what is installed in them in the library is what they can use, as well as the scripts, the code, and everything else that is needed to run applications. That is it. We are able to run these applications side by side, and they typically do not know about each other. That means we are dealing with isolation of the process as opposed to isolation of the machine. The third thing that we should be aware of is about how these resources are accessed. So with our type 1 hypervisor, we are creating different machines out of our server, and that is mainly where the interactions are happening. We are interacting with what we think is hardware, but that is being managed for us by the hypervisor. However, with containers, we are using a number of features, but I just want to draw your attention to two features of the Linux kernel that are allowing this illusion of isolation for process. The first one I want to bring up is namespaces. This is what allows the customization and the appearance that each instance of the container has its own operating system. Then we have C groups, which are responsible for monitoring and metering out our resources to make sure that we never tax our system with containers. We are limiting the amount of resources they are accessing. We are monitoring things and are able to control exactly what each container has control of. So we have granular control over the resources that are flowing to our containers. Whereas in our hypervisor, we only have the isolation of our different machines, which is much coarser. The fourth and final thing to discuss is this difference in portability and flexibility. With our virtual machines, we have what I like to think of as infinite flexibility of our hardware. This is because we're making different machines out of our server. We're saying this is how many processes that I want this machine to have, and this is how much DRAM I would like it to have. We're able to be pretty flexible about the kind of system we are building. With containers, we have infinite portability. This is because we have our container being defined in a single file, which many people know as a Docker file. We essentially have a few lines of text saying exactly how to build a container, how to run our container, what libraries are necessary, what steps to take to build our container up. We take this one file and we run it on our machine, and we can spin up our application. We store it in a repository somewhere else, which enables us to run it on different machines. We can take our file, our one file, and make it run pretty much wherever. There are no hardware limitations. Well, it's possible you might experience a hardware limitation if you specifically built your container for ARM or x86. But aside from that, you have an amazing amount of flexibility with respect to containers. There are several types of virtualization and hypervisors. We have been talking about type 1 virtualization, or what is called type 1 hypervisor. It is a hypervisor sitting right on top of hardware. Then there is type 2, and it sits a little bit higher. This is possibly the kind of virtualization that some of you may be used to interacting with. This would be something like VirtualBox or Parallels. We can take the flexibility offered by our lightweight type 2 hypervisor and the portability afforded by containers and run them together. We are beginning to see technologies around virtual machines maturing, like with KubeVirt. We are seeing newer versions of Kubernetes and OpenShift where we can run virtual machines and containers not as competing technologies, but as technologies that can work together. Of course, this will depend on the use cases involved. Remember, virtual machines were created for servers and containers were created for lightweight data portability. They are different things and they have different strengths. When we mentioned on a previous slide that things are changing when it comes to VMs and containers, let's focus on that a little bit. And remember that there are some realities that we should remember about the two different technologies. When it comes to data portability, containers are lighter weight and provide enhanced business benefits in numerous areas. Containers have greatly reduced overhead compared to virtual machines. Containers can be spun up much more quickly than virtual machines. Containers can deliver enhanced isolation and security compared to virtual machines. Containers deliver greater, easier data portability than virtual machines. And containers are less costly in numerous areas than virtual machines. Many businesses are finding containers to provide great advantages in DevOps, batch computing, lightweight platform as a service, and microservices. When it comes to data portability, VMs are somewhat inefficient, whereas containers are highly efficient. VMware has been optimized for servers, while containers are optimized for storage.